Hi everyone, my name is NaSiya Taylor and my lab partner was Mikayla Martin, and this is our MSH2 project presentation. So just some quick background about MSH2. MSH2 is a gene that provides instructions for making a protein essential for DNA repair. And the DNA needs to be repaired because sometimes there's errors that occur in the copying of DNA. And MSH2, the gene, is a part of a set of genes involved in mismatch repair. The objective of our MSH2 project was to see how a SNP in the plasmid will affect the mutation rate of a yeast strain with mutant MSH2 and plasmid DNA with wild type MSH2. So here's our plasmid extraction and digestion lab. We had three strain samples of A through C for the E. coli. We had concentrations ranging from 300 to 1950 nanograms per microliter and a ratio of 260 over 280, with our ratios coming down to between 1.82 and 1.90. And all of our ratios were pretty much close to 1.8, so we can concur that the strains were pure, the E. coli strains were pure. And then we had the sample name of PRS413 digested with APAL and XPAL, and then PMSH2 digested with APAL and XPAL. 2 fragments for each, and you can see the predicated sizes at the bottom right corner. And the goal of this lab was to isolate the plasmid DNAs from the 3 E. coli, then measure the concentration of them of our DNA samples. And like I said, we came to the conclusion that the E. coli strains were pure. And then you can see our band sizes, which just go back to our E. coli strains. You can see that there were a lot of thicker bands and darker bands, so that just indicates larger fragment sizes. Thinner and lighter bands indicate smaller fragment sizes. And here is our PCR digestion and mutation identification lab. The goal of this lab was just digest the 3 PCR products using a restriction enzyme, and then distinguish the mutant MSH2 from the wild type MSH2, and then to run those digested products on agarose gel to determine which plasmid DNA contain the mutant MSH2 insert. And then we use 3 samples of A through C again, and then we digested samples A through C, and then we use undigested samples of A through C as well. We had estimated fragment sizes ranging from 0 all the way up to 900, and the most fragments we had were started at 0 and all the way up to 2. And so we came to the conclusion that considering that the wild type did not contain any mutations, it should not contain any mutations, it shouldn't have the extra fragments that are shown in mutant 3. The fragment size and numbers should be similar to the results of B and C because those samples have the mutants, so similar results should be present for the chart above, which you guys can see right here. Next is our yeast transformation lab, which had constant parameters of temperature, formation time, and the amount of each sample. The independent variable was yeast strain AGY75, and the dependent variable was growth. And then you can see our 2 pictures. To the right, we have our plasmid, and then our PMSH2 mutant 3. The goal of this lab was to transform the yeast reporter strain AGY75, which already contained PSH44, with our mutant PMSH2 plasmid, PMSH2 prime. And as you can see with our PMSH2 mutant, there appears to be approximately 250 colonies the colonies were able to grow in the addition of PMSH2 mutant because the environment or the plasmids provided everything needed for the yeast to grow. For example, if the environment did not have histidine, tryptophan, or uracil, there was a pathway provided in order to get histidine, tryptophan, or uracil. Here's our FOA lab. Next, we had constant parameters of temperature, concentration variations, and the amount of each sample. The independent variable was plasmid type, and the dependent variable was growth. And you can see our pictures along with our chart to the right. The goal of this lab was to use FOA, fluoric acid assay, to measure mutation rate in yeast strain AGY75, transformed with either PMSH2, PMSH2 prime, or PRS413. The amount of FOA plate growth is essentially very similar in each of the stands based on their concentrations. The OD1 concentrations had no growth, whereas the OD 0.1 concentration has some growth on each. The OD 0.01 concentration had a tiny amount of growth too, and the concentrations had more of an effect on the growth than the yeast strains. Based on the results of the OD1 concentrations, they did not allow any growth, and the OD.1 concentrations have the best representation of growth. PMSH2 prime has more growth than PMSH2, and PRS413 has more growth than PMSH2 prime. And here you guys can see that if there is MSH2, then GT 6.5 ur3 is there as well, and ur3 enzyme is there, which then leads to the toxin, which leads to no growth, and then just the rest going down are just some of the pathways as well. AGY75 carrying PRS413. If there is no MSH2 present, then the GT 16.5 is not there, and then the ur3 enzyme will not be present as well. The toxin will not be present, which will lead to growth. Like I was saying, the AGY75 carrying PMSH2 has the lowest mutation rate. AGY75 carrying PMSH2 prime has the medium mutation rate, and then AGY75 carrying PRS413 has the highest mutation rate. So how does this connect to our mutant and gamete research paper? The mutant identifies with MSH2 G693S, which affects the class of ATPase. So this is just the MSH2 gene that I just mentioned is just a mutation that has dominant mutator effects, and the class of ATPase is just it just affects how which like proteins will carry in that ATPase. So, and then here is our works cited, and that's all I have for our presentation. Thank you guys for listening.